Am I audible?
Yes, sir, you are audible.
I want to give some instruction about the test. We will conduct the test on the last day of the FDP. It's of 30 question and is based upon the session. It's of all MCQ types of about 30 minutes. And please submit the feedback also on the last day of the FDP. It is mandatory. So two things are mandatory. First, to attempt the test and to give the feedback. One another thing is that you have to submit also the reflective journal feedback, which will be given from the for the at the last day on the Google form. It will be shared on your WhatsApp group and also through the email. If any participants have any query about the test, about the attendance, about the feedback procedure, they can ask. Time of test is given in the schedule also. I think it's between 6 to 6:30. And please check your name on the Atal portal because certificate will be generated through Atal portal, not by us. Am I audible?
Yes, sir.
Now, now moving ahead to the FDP, we are honored to have with us Dr. Liladhar Malviya sir, which is my guru, supervisor, and my mentor, is with us. I am so blessed today. On the behalf of AICT Atal Academy and from MIT Group of Institute Ujjain, I welcome Dr. Liladhar Malviya sir, Professor Electronics and Telecommunication Engineering Department, the GS Institute of Technology and Science, Indore. To formally introduce our esteemed speaker, I now invite his student, Dr. Rashmi Pant, Assistant Professor, ECE Department, MIT Ujjain. Dr. Pant, kindly take the virtual stage and introduce our today's speaker, Dr. Liladhar Malviya sir. Over to you, Dr. Pant.
Thank you, sir. Good evening, respected faculty members, colleagues, and participants. I am Rashmi Pant from ECE Department, Mahakal Institute of Technology, Ujjain. It is my honor to welcome you all to this online faculty development program. I believe today's session will be a valuable chance for all of us to learn new perspectives and refine our skills. We are especially fortunate to be guided today by someone who has not been just an academic authority, but also a mentor in my own journey. Dr. Leeladhar Malviya sir is a distinguished professor in the Department of Electronics and Telecommunication Engineering at SGS Indore. He obtained his PhD from IIT Roorkee and completed his earlier degrees in related fields. Dr. Malviya's research expertise includes the design and development of antennas across advanced wireless communication spectra. His areas of interest are microstrip patch antennas for 4G, 5G, and terahertz, ultra-wideband antennas, substrate integrated waveguide antennas, millimeter wave antennas, and vehicular communication antennas. He has published extensively in high-impact SCI journals and contributed reviews and innovations in emerging antenna technologies. Notably, he is the co-author of the book MIMO Antennas for Wireless Communication Theory and Design. He has also served in key academic leadership roles, including as the IEEE General Co-Chair of the 11th International Conference on Communication Systems and Network Technologies, CSNT 2022. He has published more than 200 research papers in reputed SCI index journals, book chapters, and international conference proceedings. His research contributions have been widely recognized, with over 1,700 citations, an H-index of 22, and an I-10 index of 32. He has also contributed as a reviewer for reputed international journals, including the IETE Journal of Research, IEEE, Wiley, and elsewhere. He has actively contributed to the academic community, serving as a session chair and organizing committee member in more than 20 national and international conferences. He is an active member of several professional societies, including IET Life Member, IE, IST, and IEEE. It is truly my great fortune and privilege to have him as my supervisor and mentor. Now, I invite Dr. Leeladhar Malviya sir to address the participants. Over to you, sir.
Thank you so much, Rashmi and Mohit, for the kind invitation to deliver the lecture on the 5G and terahertz MIMO antennas. Good evening, everyone. Hope that I'm audible to everyone.
Yes, sir.
Okay, thank you so much. And I'm happy that you are enjoying with our lectures. Most of the academicians and researchers are delivering the lectures from all over the world, and hope that in future you will also do the research with these all the researchers and the guides. So today I'm starting with the 5G and 6G antennas for the next generation communication. This lecture is dedicated to just wait, please. Is screen is visible completely?
Yes, sir.
Okay,
It's
thank you
visible.
so much. So this lecture is dedicated to my professor, Dr. Vinita Chaudhary ma'am. She died in COVID during 2021, and another, my friend, Mr. Anurag Srivastava, who died due to the cancer in 2019. So these were my true inspiration, and I'm dedicating the whole lecture to my professor and colleague. So now let us start with the wireless communication. As everybody knows that the wireless communication is possible because of the multipath propagation. And in this multipath propagation, we may find line of the sight communication as well as the non-line of the sight communication. So this non-line of the sight communication can be seen because of the refraction, diffraction, and the scattering. So because of this line of sight communication, because line of sight communication is a direct path between the transmitter and the receiver, and the non-line of sight communication is because of the multiple paths due to refraction, diffraction, and the scattering. So anyhow, you are able to get the signal. But the question is that what must be the strength because of these all the paths? So if you look at the direct wave, so signal strength is maximum at the receiver if the signal is received through the direct path, and that is the line of the sight communication. But this is not the true scenario, because both the transmitter and the receiver cannot be in the same line or on the same location, and that's why the signal will reach through the refracted or diffracted paths. So if you look at the signal strength using the refracted wave or diffracted wave, so signal strength in these two cases is very much less than the direct wave. And finally, the composed signal can be seen here. So composed signal, and then finally when you reconstruct the waveform, so that may be similar to the original signal. So in that case, slight degradation in the signal strength can be seen But the question is that how these direct paths or the non-line of the sight communication are able to show the delays. So delays in case are variable. So now in each evolution in the wireless technology, the most important part was that how to increase the data rate. So if you look at the first generation, so first generation was started with the 2.4 kilobits per second, and voice calling was started with the first generation. So if you move ahead from the first generation, you can find that in 2G, 64 kilobits per second was the data rate, and the SMS was started along with the voice calling, and in third generation, the data rate was increased to 2 megabits per second, and so many things were connected using the internet. And in fourth generation, the expected data rate was 1 gigabits per second, but it was unable to achieve because of the limitation of the antennas and so many other factors. And in the 5G, it is expected that the 10 gigabits per second of the data rate can be obtained. And in this case, you can find so many services. So we'll see those are the things and how these 5G antennas can contribute to the higher data rates. And in the 6G, the whole world can be connected, and complete AI use can be seen in the 6G. So let us look at the evolution and the vision in wireless technology. So if you look at the 4G, so 1 Gbps was the highest data rate. In the 5G, it is expected that the 10 Gbps of the data rate can be obtained, and in the 6G, 1 Tbps of the data rate is expected. But this is not the true scenario because there are so many limitations. And if you look at the end-to-end delays, so 100 millisecond of the delay was in the 4G, and in the 5G, 10 times reduction in the delay can be seen. And in the terahertz, you can expect the again 10 times reduction of the end-to-end delay in comparison to the 5G. But the question is that how you are able to get these higher data rates. So higher data rates are dependent on the spectral efficiency, and this spectral efficiency can be obtained in terms of the data rate and the bandwidth or frequency. So maximum spectral efficiency that can be seen in case of the 4G is 15 bits per second per hertz. In case of the 5G, 30 bits per second per hertz, and in the 6G, 100 bits per second per hertz. And another question is that how the AI is used, or where the AI is used in this technology. So 4G is completely free from the AI, but 5G is partially using the AI, and the 6G is completely enabled with the AI. So here, if you look at the frequency range for the 4G, so we can find that the 6 gigahertz of the frequency, and this 6 gigahertz includes the WLAN and the MIMAX and the LTE frequency bands. And in the 5G, we have the two different spectrum ranges. So one is FR1 and another one is FR2. So FR1 is up to the 7 gigahertz range, and FR2 is up to the 90 gigahertz range. But in case of the 6G, this 10 terahertz of the frequency range can be expected from the 0.1 terahertz to the 10 terahertz. So now if you look at the different generation and the communication technologies, so the beamforming and the massive MIMO, these two are the most important part in the 5G. And Li-Fi and the wireless sensor networks are also two important aspects of the next generation wireless technologies. And another things about these technologies are that the intended coverage, bandwidth on demand, video on demand, higher data rates, beamforming, multi-user MIMO. So these are the demanding things. But the question is that how these technologies are used, what are the drawbacks of these technologies? So Li-Fi is hazardous to the biological and the non-biological things, and that's why its use is limited. And if you look at the wireless sensor networks are especially used in automotive, manufacturing, oil, and the gas sectors. And for the productivity in the forecasting, wireless sensor networks are used. So many companies are investing in these next generation wireless communication like the Cisco, Huawei, Ericsson, Samsung, Nokia, etc., etc. So if you look at the another things which are expected in the next generation, so these are the autonomous driving, location-based services, vehicle-to-vehicle communication, intelligent transportation systems, and the another most important part in this autonomous driving and all is the anti-collision system. So if you look at the car of the Tesla, so Tesla has taken so many tests and working on the anti-collision driving systems. And another things about the next generation are machine-to-machine learning, machine-to-human interfacing, artificial intelligence, machine learning. But the question is that what must be the bandwidth for these all the things? So huge amount of the bandwidth is required, and the higher data rates are required for this machine-to-machine learning, AI, and the ML. So the another thing which is important for the frequency spectrum is that the frequency spectrum must be saved, because most of the money goes to the frequency or spectrum auction. So the money must be saved by saving the spectrum. So research is going on to save the spectrum also. And there is a demand of the high gain antennas, directive antennas, high data rate antennas, large bandwidth are required. So in the 4G, you have the 5 megahertz, 10 megahertz, or 20 megahertz of the scalable bandwidth. But in case of the 5G, you have 100 megahertz of the bandwidth under the 7 gigahertz of the spectrum, and more than 1 gigahertz of the bandwidth under the higher frequency spectrum or FR2 band. And there are another things like the lightweight antennas, compact antennas, and higher values of the front to back lobe ratios, and the low value of the mutual coupling. So mutual coupling is seen in case of the MIMO antennas, multiple input, multiple output antennas. So now another things about this next generation of the communication, that when you want to design the antenna, so in that case the substrate and the conducting materials play the very important role, because the efficiency is completely dependent on the substrate and the conducting materials. So now let us start with the CISO and the MIMO antenna. So in case of the CISO antenna, that is known as a single input, single output. Am I audible to everyone? Anybody, please?
Yes, sir.
Okay, thank you so much. Okay, so in case of the single input, single output antenna, you have a single antenna at the transmitter and a single antenna at the receiver. And such type of communication is seen in case of the line of the sight communication. So when the signal is lost, receiver is unable to receive the signal. So in such cases, multiple antennas at the transmitter and the multiple antenna at the receiver can provide the faithful communication, continuous signaling, reliability, and higher data rates. So how we can compare the CISO and the MIMO? So let us look at the scenario here. In this table, I am showing that 1 Gbps of the data rate is also possible with the CISO, but the higher amount of the bandwidth, like the 250 megahertz is required if you have the spectral efficiency of the 4 bits per second per hertz, right? And the same thing can be obtained, 1 gigabits per second of the spectral efficiency can be obtained in the MIMO antenna if you have the 50 bits per second per hertz. So in that case, the 20 megahertz of the frequency band is required, and you can save the frequency spectrum 10 times of the CISO antenna. This MIMO antenna works on the parallel communication, and the CISO is there is a single antenna as the transmitter and the single antenna at the receiver. So serial communication can be done with the help of the CISO antenna. So in that case, the delays are higher, and in the MIMO, due to the parallel communication, you can find a higher amount of the gain and the reduced delays. And if you want to increase the data rate in the CISO antenna, so in that case, with the variation in the bandwidth, you can find the variation in the data rate. But if you look at the data rate of the MIMO antenna, so with respect to the 2x2 MIMO antenna or 3x2 MIMO antenna, and with the bandwidth of the 40 megahertz or 80 megahertz, you can find 2 times of the data rates in comparison with the CISO antenna. So here, higher data rates can be obtained with the help of the MIMO antennas. And if you look at the capacity, so the formula of the capacity can be obtained with the help of the Shannon-Hartley theorem, and that is given by the bandwidth multiplied by the logarithm of the 1 plus SNR. So when you want to get the higher capacity, so in that case, you have to increase the signal to noise ratio. But if you look at the MIMO antenna, so capacity of the MIMO antenna depends on the number of streams, and these number of streams can be obtained with respect to the number of transmitting and the number of receiving antennas. So suppose you have 2x2 MIMO antennas, so 4 streams are available here. So if you multiply the 4 with the capacity of the CISO, so you will be able to find out the capacity of the MIMO antenna. And if you want to increase the capacity using the power ratio, so in that case, the logarithmic increase in the capacity can be obtained in the CISO antennas, whereas the MIMO antenna, linear increase in the capacity can be seen. And signal to noise ratio in case of the MIMO antenna is n times of the average signal to noise ratio, whereas signal to noise ratio is limited in case of the CISO antenna. And spectral efficiency is very high in case of the MIMO antennas. Similarly, the frequency reuse plan and interference reduction, these can be easily done with the help of the MIMO antennas. So CISO works for the line of sight communication, and the MIMO is a solution of the multipath propagation. So there is a graph here that capacity in the MIMO will increase with the linear fashion, and the capacity of the CISO, CMO, or MISO will increase in the logarithmic fashion. Now, this is a generalized structure of any of the wireless communication system, where the number of antennas are seen at the transmitting end and number of antennas at the receiving end. But if you have the multiple receiving antennas, so each user may have the multiple antennas, and using such a scenario, you are able to find the multi-user MIMO antennas. So in general, we deal with the single user antennas, a single user MIMO. And if you have the multiple antennas at the transmitting end and the multiple antennas with each of the receivers, so in that case, you can find the multi-user MIMO antenna. So now let us look at the impact of the MIMO antennas with the modulation techniques. So if you are implementing the signal processing part or communicating part, so in that case, if you use the different modulation techniques, so with respect to the 1x1 or 2x2 or 3x2 MIMO antennas, you can find the variation in the data rate. And if you increase, for example, you have the 16 QAM. So for the CISO antenna, for the coding of 1/2, you have the 130 bits per second per hertz of the data bits per second of the data rate. But if you go through the 2x2 or 3x2 or 4x4 MIMO antennas, so you can find the double of the data rate can be obtained with each of the modulation technique. So now, if we move ahead and look at the evolution in the wireless technology, so we can find that there are so many expectation with the new generation, like the energy efficient antennas must be there, reconfigurable antennas must be there, scalable adaptive antennas should be designed, AI and the machine learning based antennas should be designed, or wireless, wide angle scanning array antennas must be designed. And the new research is going on throughout the world on the holographic antennas, metamaterial antennas, flexible, variable antennas. So these are the new things which are expected in the next generation of the wireless communication using the antenna technology. So now let us look at the 5G antenna requirements. So 5G is a project of the 5G triple P. So this 5G triple P is a 5G infrastructure public-private partnership project. And this is a joint venture of the third generation partnership project. So third generation of the partnership project is a part of the 4G. So jointly, this third generation partnership project and the International Telecommunication Union and the European Telecommunication Standard Institute and the 5G infrastructure public-private partnership, these are jointly providing the standards to the world. And their aim is to provide the applications to the smart homes, buildings, smart cities, 3D video, work in the play in the cloud, remote medical services, virtual and augmented reality, and the massive machine-to-machine learning, as well as the high quality of the services are expected with the traffic separation and with the resources reservation and for the service-specific configurations. So now, these are the things we have already covered. So let us move ahead. There are two spectrums, the 5G frequency bands. So one is the FR1, so that is the lower frequency spectrum, and it start with a 4.1 terahertz to the 7.125 gigahertz. So earlier this band was up to the 6 gigahertz, and now this has been extended up to the 7.1 to 5 gigahertz. And the other frequency band that is known as FR2. So it is starting with the 24 gigahertz, and the maximum frequency range in this FR2 spectrum is 90 gigahertz. So most of the countries like the China, Korea, Japan, and even India, these are making the antennas for this higher frequency range. And if you are going towards a high frequency range, so definitely those can be assembled in the ICs only. And still, there is no end of the frequency, because this time we are also working on the terahertz spectrum. So so many applications are available for the terahertz spectrum. So there is no end of the frequency bands. Now, if you look at the 5G applications, so these are divided in so many categories like the augmented, dedicated, autonomous, interconnected, revolutionized, then virtual, tactile, super efficient. So these are the frequency bands are used in these different applications. And if you look at the division of the frequency band, so 5G is completely dependent on the two spectrums. So especially the 5G and the millimeter wave band is used for the 5G, and the mid band is also used in correlation with the 4G in 5G. And the mid bands or the lower bands are used with the lower generation. So there is an interoperability, because the previous generation should not be ignored, and that's why the 5G combines the role of the all the previous generations. Now let us come to the array antennas, because arrays and the MIMO array antennas are the most important part of the 5G antenna designs. So if we talk about the arrays, so arrays are used especially to increase the directivity, gain, and signal to noise ratio. And these are used to shape the radiation pattern of the antenna, and also cancel the interference in the undesired direction. And also, if you look at the other scenarios of the antenna arrays, so most important part of the antenna array, that this is made with the help of symmetric or asymmetric type of the patches in case of the microstrips. So these arrays are used in the broadcasting, beamforming, naval applications, phase arrays, radio frequency identification, weather monitoring, missile guidance, and fire radar aircrafts. So if you want to use an array, so these can be designed with the help of the different structures on the microstrip, and microstrip patches are used. So this antenna, series fed antenna, we have designed using the 6 elements, and we have used here 50 ohm of the stub and 70.7 ohm of the quarter wave section, and the inside feed was used, in this design. So if you look at the S parameters, return loss here, in first step, when the single element is used, you can find the very low value of the return loss. And when you use the 6 elements, so very, again, the return loss can be lowered, and this may be around minus 40 dB. So arrays are used to reduce the losses. That means interference can be reduced and the gain can be increased. So this is one of the case here. But if you do not have the proper matching in your design, so in that case, the radiation pattern may be dispersed, means the wide lobe radiation pattern can be obtained. So if you look at another scenario here, so what we are doing here in this second design, we are reducing the size of our antenna. So we are using the folded lines, and as we want to increase the bandwidth, so we are using the tapered patches here. So if you look at the shape of the patches, so these all the patches are dissimilar here. If you look at the different steps of this antenna, so this is a series in the parallel connection of the tapered array antenna, so which we have designed for the 28 gigahertz of the applications. And if you look at this delay lines, so these are the folded delay lines. By using the proper design of the delay lines, you can make the proper value of the phase shifters, like 45 degree of the phase shifter, 90 degree of the phase shifter. So these phase shifters are used to shape the beam, right? So if you look at the beam here, or the radiation pattern here, so you can find here that that is very close to the center value of this design array in the step 4. And in these steps, you can find that in each step, you are getting the reduced value of the return loss. So if you have the very low value of the return loss, so losses can be less in such cases. Now look at another scenario. We are using the series and parallel tapered array antenna for the 28 gigahertz of the application. We are using here the 50 ohm of the stub, and insert feed here, and the lambda by 4 sections here are the 70.7 ohm lines here, and there are the chopped opposite corner faces of the patches. If I ask the question to the audiences that what is the role of the chopping of the antenna, so is there any answer, any opinion? Anybody please? What the chopping is done in the antennas? Anyone? No?
Anyone from the participants like to answer?
To get circular polarization.
Okay, correct. That we are using the chopping to get the circular polarization, but these are the linearly polarized antennas, because if you want to use the circular polarization, so in that case, you have to adjust the value of the axial ratio. So here, there are two things about the antennas, that if you get the elliptical polarization, so the chopping can be used to convert the elliptical polarization into the linear polarization. So there are two uses of the chopping. One is the elliptical polarization can be converted into the linear polarization. So these are the linearly polarized antennas, and chopping can also be used to make the circularly polarized antennas. So there are these are the two important things here. And if you look at the shape of the patches, so again you can find here the tapering is done here, means each of the patches are different in the shape and the size. So this is used to increase the bandwidth. And if you look at the shape of the radiation pattern, so completely the whole energy is concentrated at the center. So with the properly designed antennas, or with the proper impedance matching, you are able to find the proper shape of the radiation pattern. Now let us come to the MIMO array antennas. So if you look at the MIMO arrays antennas, so this paper was published in the 5G millimeter wave application for the beamforming, and in the wireless personal communication in 2022. So what was the purpose of this antenna? That how to utilize arrays and how to convert that array in the MIMO antenna. So if you look at the shape of this array here, so there are 1 cross 12 elements here, are the 12 blocks here at each port, and the design was of the 2 cross 12 elements. So the ultimate aim was, of this design was to provide the signal or to provide the operating bandwidth at the 28 gigahertz application for the 28 gigahertz application. So full ground was used here. And if you look at the different steps here, so in final step, you are able to get the very low value of the return loss, around 46 dB of the return loss can be obtained here in the final step. So this is these steps are started with the rectangular patch antenna. Then this rectangular patch antenna is converted using the stub matching. Then the blocks are used in the third step, and the number of blocks are increased in each step. And finally, the MIMO array antenna has been formed. So we have obtained a very high value of the MIMO array antenna. So the gain was around 26 dBi. So if you look at the other aspect of the MIMO antennas, when you want to design the MIMO antenna, so another important parameter, one is return loss, and another important parameter is the envelope correlation coefficient. So if you want to get the envelope correlation coefficient, then definitely you can use the S parameters, or you can use the electric field here, or the E field here, to find out the envelope correlation coefficient. And if you want to get the envelope correlation coefficient in terms of the S parameter, so all the return loss and the isolation parameters are used to find the value of the envelope correlation coefficient. This is the very important diversity parameter to show the value of the envelope correlation coefficient, though the isolation is sufficient to show the value of the mutual coupling or the isolation between the radiating ports. But the ITU has standardized the term envelope correlation coefficient, and the maximum value of this envelope correlation coefficient is 0.5. So in each of our designs, we obtained a very, very low value of the envelope correlation coefficient in the range of 10 to the power minus 3, 10 to the power minus 4. Now let's come to the another thing that is very important in terms of the diversity parameter, that is known as the mean effective gain. So if you want to get the mean effective gain, then definitely you must have the multi-ports like the MIMO antennas. So you must have the cross polarization ratio, you must have the power spectral density, you must have the gain in azimuthal as well as in elevation direction. So using this, you can find the mean effective gain. So for the indoor application or for the outdoor application, you can use the Gaussian environment or the uniform environment, and you can find the value of the mean effective gain. And this must be less than or equals minus 3 dB. Okay, similarly, if we are interested in finding out the value of the total active reflection coefficient, so we must have the knowledge about the excitation angles at the ports. So if each of the port has a different excitation angle, so in that case, we can find that how much power is radiated or reflected from the ports. So this can be obtained in terms of the total active reflection coefficient. So using the total active reflection coefficient, we will find the value of the radiated power or the reflected power as well as the active bandwidth. Now let's come to the MIMO array antenna gain. So as you have attended the lecture of the Dharmen Singh sir, and he has disclosed so many things about the antenna, basics of the antenna. So we have here this PR is the received power that can be obtained in terms of the transmitted power gain of the transmitting antenna. So this transmitting antenna is connected to the microwave generator, and this has the known gain, and receiving antenna. So substitution method or the replacement method is used for obtaining the gain of the antenna and the wavelength of the antenna. So as Dharmendra Singh sir also suggested that if you want to use the low frequency of the application, so the distance between the transmitting antenna and the receiving antenna must be around 1 meter. And if you want to use the 28 gigahertz of the application, so in that case, the distance between the transmitting antenna and the receiving antenna must come in the centimeter and in millimeter. So please remember these are the things. So using these are the approaches, the Freeze equation, we are able to find out the gain of the MIMO antenna, and the directivity can be obtained if you have the beam width using the radiation pattern. So theta E and the theta H for the electric field and for the H field. So using these two, you can find out the value of the directivity. And this directivity, if you look at the relation between the gain and the directivity, so D is proportional to the G. Sorry, G is proportional to the D. So in that case, gain can be equal to the directivity, but the efficiency is the deciding factor, and this efficiency depends on the radiation efficiency, mismatch efficiency, conduction efficiency, and the dielectric efficiency. So whenever you want to design any of the antenna, you must have the knowledge about the loss tangent. If the loss tangent is very low, so you are able to find out the higher value of the gain and the higher value of the efficiency. So if the loss tangent is very low, then this is possible. And if you are using, for example, FR4, this fire resistant substrate, so in that case, the loss tangent is 0.25, right? So this 0.025 around value is very high, and loss tangent of the Rogers 580 is around 0.0009. So because of the very low value of the loss tangent, the substrates will become very costlier. So the Rogers 580 substrate can be available from the market using the 8 to 10,000 rupees per square feet, and the FR4 substrate can be obtained around 500 rupees per square feet sheet. So these are the costs associated with the loss factor, and the loss factor is very important to decide the efficiency and the gain, because this gain is decided with the help of the directivity and the efficiency. So now this MIMO array antenna we designed for the beamforming application. So you are able to see here that the two antennas are showing the radiation at the +20 and the -20. So please remember that the MIMO antennas are by default the beamforming antennas. So MIMO antennas are by default the beamformers, and in case of the arrays, you have to make certain arrangements to find out the beamforming. So you'll see later on about the beamforming approaches using the arrays. Now let us come to the second design. So this was the simplest design we have communicated in the conference. So structure was having the 8 elements to each of the port, and these 2 elements are connected in parallel with the help of the 50 ohm line. Similarly, we have designed the another antennas here, and those antennas were generalized in the shape. So generalization means by changing the radius of the patches, you are able to find out the shifting of the whole band. So by using the generalized structures, we are able to shift the bandwidth, complete bandwidth, or the complete frequency band or the operating band from the higher to the lower value. Now look at the another scenario here, that how the 5G can be enabled with the beamforming. So beamforming is one of the most important approach. With the help of this beamforming, you are able to cover the particular user, the particular direction, or the particular building. So this is just like the traffic signaling system where the beam is focused to the particular direction for the required time or for the intended application. So this beamforming has the main beam radiation pattern and the very low side lobe levels. So the beamforming is specially used to nullify or reduce the value of the side lobe levels. So this is especially used in the radar, seismology, biomedical, sonar, and the IEEE 802.11 SE standard. And if you look at the another benefit of the beamforming, that the signal to noise ratio can be increased because the back lobe reduction can be seen in the case of the beamforming. So with the reduction in the back lobe, the front lobe at the main beam can be increased, and the higher value of the gains are expected in case of the beamforming. So this beamforming application can be completed with the help of the proper phasing and the proper amplitude of the signal added constructively or destructively. So beamforming is an approach that can be designed with the help of the active beamformer and with the help of the passive beamformer. So in both the cases, you steer the beam so that the particular direction can be covered. So let us look at the beamforming approach here. Let us look at first that you have the conventional array. Let the 2-3 elements are connected in the series or in the parallel. So the conventional array provides a wide lobe radiation pattern. And in case of the beamforming, the beam is directed to the desired direction towards the intended user. So in that case, the pencil shape of the beam can be seen with the help of the arrays. But how this beamforming can be done with the help of the arrays? So look at this another scenario here. If you have the one radiating element, so this one radiating element is able to provide the wide lobe of the radiation pattern. But if you have the two similar or the dissimilar type of the elements, and these are fed with the same phase, so in that case, a wide lobe is converted into the narrow beam, and the main lobe can be seen in a particular direction with the slight side lobe levels. But if you increase the number of elements in the array from 2 to 4, and if you fed them with the same phase, so in that case, a very narrow beam of the radiation pattern can be obtained with a very low value of the side lobe levels. So this main beam is very narrow and having the very high gain. So if you increase the number of elements in the array, you can increase the gain, you can shape the radiation pattern, you can reduce the side lobe level, you can increase the front to back lobe ratio, and you can increase the directivity. But the question is that there must be certain saturation. You cannot increase the number of elements in the array randomly, right? So please remember these are the things. Now let us provide the feeding with the help of the phase shifters. So let us assume that you have the 4 elements, and if you fed the 4 elements with the help of the frequency with the 45 degree of the phase shift, so you can tilt the beam in a particular direction at the 45 degree. So a particular user or the particular building or the direction can be covered if you feed these all the elements with the help of the 45 degree. And if you make the set of the arrays, let the 2 elements in the array are fed with the 45 degree, and another 2 arrays are fed with the minus 45 degree. So in that case, the 2 beams are can be obtained, and you can cover the 2 users or the 2 directions. So beamforming is an approach which is used to cover the particular user or the particular direction. So this is most important part in the 5G, and especially this is used for the millimeter wave application. Okay, now if you want to design the beamforming antennas, so you must have the knowledge about the microwave devices or the elements used for the beamforming. So here you may have the lossless divider that is used to divide the power at the port 2 and the 3. So in most of the cases, the 50% of the power can be obtained at the port 2 and at the port 3. Similarly, you may have the lossy or the resistive power divider. So again, you can find the 50% of the power or the 3 dB of the power can be obtained at the 2 ports. Similarly, you have the Wilkinson power divider. Wilkinson power divider is the most important part of the any of the beamformer. So here again the 3 dB of the power can be obtained at the port 2 and the 3. But the question is that how to design such type of the structures. So you have the 50 ohm of the characteristic impedance. Just wait, please. So you have the 50 ohm of the characteristic impedance, but the other arms of the this Wilkinson power divider are seen as under root 2 Z0. So characteristic impedance of the other arms can be under root 2 Z0. So this under root 2 means 1.414 Z0. That means the impedance will increase by 1.4 times. And certain power dividers can be obtained with the characteristic impedance divided by the under root 2. So in such cases, you can make the baseline couplers or the 90-degree hybrid couplers. So these are also the parts of the beamformers. So here you have the branch line or the quadrupler or the 90-degree hybrid coupler. And please check here that how the design can be seen here. So you have the 50 ohm of the characteristic impedance, and in each arm, you are using the quarter wave length of the transmission line, but the impedances, characteristic impedances of the two arms and the other arms can be different. So one has a 50 ohm of the characteristic impedance Z0, and other arm has the 0.707 Z0 of the characteristic impedance. And the separation between the upper arm and the lower arm is using the quarter wave length. So these are certain important parts of the beamformers, and different kind of the beamformers you can design if you are using the delay lines. So you can use here the delay lines and the stubs here. Stubs are for the impedance matching, and the delay lines are for the reduction of the size to increase the compactness. So another parts of the beamformer are the phase shifter. So this phase shifter is dependent on the thickness of the line as well as separation are the shape of the line. So this is a phase shifter, microwave phase shifter, or the microstrip phase shifter, which is made on the microstrip substrates. And if you change the value from 0.58 to the 0.79, so you can find out the 45 degree of the phase shifter, but especially 90 degree of the phase shifters are used in case of the directional couplers. So look at the one of the application of the beamforming. So switch beamforming is here, and the Butler matrix is especially used. So elements of the Butler matrix are three important elements of the Butler matrix are: one is a phase shifter, another one is 90 degree of the baseline coupler, 90 degree hybrid coupler, and the third one is a crossover. So crossover is designed with the help of the 90 degree couplers or the baseline couplers. So let us see the design antenna which was published in the book chapter, and this was designed with the help of the hybrid coupler, phase shifter, crossover, and the two patches. Similarly, we have designed another switch beamforming using the Butler matrix. So here you can find the different types of the phase shifter here having the stub matching, and the different types of the hybrid coupler here is comparison with the previous design, and the crossover is completely different here. So you can make the different types of the crossovers, phase shifters. You can use the stub matching, you can use a folded line, you can use the different types of the 90 degree hybrid couplers, and with the help of them you can make the Butler matrix. So many designs we have done for the Butler matrix. So few are under communication, are under design. So we are not discussing those communicated or the design butler matrix here. Now, let us look at the high-speed application. So if you want to use your antennas for the high-speed applications like the vehicular communication, like the fast trains, so in that case, if you use the low frequency of the spectrum, so definitely the losses will be very high and the signaling cannot be done, or the reliability can be disturbed. So 28 gigahertz of the antennas are used especially in case of the vehicular communication. So substrate integrated waveguide technology is one of the most important part of the antenna design for the vehicular communication at the 28 gigahertz. Now the question is that why we are using this substrate integrated and what is the meaning of the substrate integrated waveguide here. So please check here, the paper was published in 2024 and this paper is of the Mr. Mohit Pant, who is the organizer of your this FDP, ATAL FDP. So SIW-based MIMO antenna with high gain and high isolation. So let us look at the shape of this antenna. Here you have the substrate. Definitely you have the substrate. And what you are doing here, you are making the cylindrical holes from pitch to the ground throughout the substrate here. So you have the substrate integrated with the waveguides. So cavity holes you can create, and you can fill the cavities with the help of with the help of inductive component like the copper wire. So when you insert the copper wire in the cavity holes, so in that case, the higher order modes can be eliminated, and you will concentrate only on the 28 gigahertz of the application. And the another thing about the substrate integrated waveguide, that this structure is especially similar to the rectangular and that circular waveguide. So here this structure, as we are dealing with the cylindrical holes here, so this is structure similar to the circular waveguide, and this why this is known as the substrate integrated, because we are shorting the page to the ground with the help of the copper wire, and which is cylindrical in the shape. So this is known as a substrate integrated waveguide. And because of this substrate integration, you are getting the high value of the isolation and elimination or the suppression of the higher order modes, because if you look at the higher order modes, the power is divided in the higher order modes, and you will not concentrate the whole energy or the whole power to the desired frequency band. There is another benefit of the this substrate integrated waveguide technology, that when you use the substrate integrated waveguide technology, so gain is concentrated in the particular direction. So gain can be increased with the help of the substrate integrated waveguide technology. And we are using here this complementary split ring resonator, because etching is done in the copper. So that's why this structure is a complementary split ring resonator. So this is a metamaterial here, and which is used to again enhance the quality of the antenna, the characteristics of the antenna in terms of the gain, efficiency, and concentrating the power to the desired band. So now, if you use this structure, so let us look at the design steps here. In step 1, you are using the step matching here with the rectangular page. In step 2, 3, you are using the cylindrical holes and shorting those cylindrical holes with the help of the copper wire. So this is the integration, substrate integration with the copper. And then you are using the rectangular slot here in between the cylindrical holes in the page. So if you cut the page, if you cut the slot from the center here, a capacitive body and the inductive body can be enhanced in the page, and that will become one of the resonator. So this CSRR structure, the SRR structure, is one of the resonator. So in our design, we used the CSRR, and that is the LC equivalent structure, parallel tank structure. So now, please check the effect of this structure on the return loss. So if you look at the step 4 here, the frequency is around 28.5 gigahertz. And if you convert the closed slot into the open loop resonator, I mean in the CSRR. So in that case, the frequency is shifted by 500 megahertz towards 28 gigahertz, and the return loss can be reduced around minus 40 dB. So this is the benefit of the CSRR and the substrate indicated waveguide technology. So this was a fabricated structure. We have taken the measurements with this fabricated design, and here if you look at the type of the ports, so these are either the south end or the west end or the end launch connector type of the ports. Can I ask the question to the audiences? What must be the cost of these ports? Anybody, please? Anyone? No?
16,000. Repeat the question, please.
What must be the cost of the ports?
16K.
Pardon?
12,000.
Yeah, so this time this is around 4 to 8,000. And Ali, just a minute.
The copper casting is there.
The copper, actually that is uniformly distributed.
Yeah.
So,
In one design, we can find out there is a square shape, a patch antenna design, and other. And in the second design, B part, you are
rectangular shape.
yeah, rectangular shape having some space in between, and it's a center feeded antenna.
Yes, this is the center feed.
Okay, and in our second design, we find out that there is no patch in between this all the holes you are designed.
No. Actually, this is the front end. Another part is the back.
Okay, fine. Sorry, sir. In the second design, we find out that there is a space between us. The hole is having a gap in the hole.
Okay, that is not properly means filled structure.
So that provides some losses also, sir, because it is not.
Definitely. If the designs are, I think some mobile is very close, so I'm getting a double voice.
So now you can speak, sir.
Okay, thank you. Now this is clear. Yes, please ask the question.
Yes, Dinesh, sir.
Sir, in the first design, I thoroughly reviewed that in the top side where the scale parameter is from 5 to 6 mm, 5 to 6 centimeter. There is in the first A design, in the 5 to 6 in between the whole shape. There is some fault is there, and in the second design we find out there is in the whole shape there is some defect is there, so it is provide in the return loss it get effect.
Definitely. But please remember this part A is the front and the part B is the back of the same antenna. Clear?
Yeah, that's clear, but it effect on
Yeah,
some gain parameter
definitely.
or not? So that's why that's
Definitely,
what I.
this will affect the parameters also. Return loss is affected, and certain
But
losses can be seen
but
in the
in which
game.
frequency band this antenna works?
This is for the 28 gigahertz application.
Okay, isn't it? Actually, I want that somehow that the hexagonal shape, octagonal shape works on C band, KU band. That particular band, I want to know that MIMO antenna also work in so for max communication also or some that's
Yes. But please remember that when you want to use antennas for the low frequencies, right? So FRC dielectric substrate is sufficient. I think double voice is coming. Mohit.
Yes, sir. I have mute off the microphone. You can
Okay.
speak now.
Okay. Hello. Is it clear now?
Yes, sir.
Okay. So please remember that when you want to use antennas for the lower frequencies, there is no problem, and thickness of the copper is around around 70 micrometer, right? And in case of these antennas, the thickness of the copper is 0.0175 mm or 35 micrometer. So if the antennas are not properly designed, when you have the substrate indicated waveguide technology and the copper is not properly filled in such antennas, so definitely the losses will increase. But at the high frequencies, if you are using the low loss tangent of the dielectric material, so losses can be minimized, right? So can I move further? May
Any
we move
queries
further?
from the participants?
can I ask
I have
something,
few
sir? Because
doubts,
my
sir.
mic is already off, sir.
You can write question in the chat box. So I will ask to sir, because
Sorry, sir.
there is background noise.
Okay, shall I move further?
Yes,
I
sir.
have one doubt in this slide.
Yes, please.
Sir, already this antenna has been designed at 28 gigahertz.
Correct.
So dimension has been made for 28 gigahertz only.
Right.
Okay. So once it once it got resonate at 28 gigahertz, then what is the necessary for making this CSRR in the patch?
Actually, these are the different technologies we have joined together here, because the research work in this generation or for the next generation is going on the metamaterial and the SIW. So we have joined these all the things together, right? So especially the CSRR or SRR are used, and these are the metamaterials. So metamaterial based application we have designed.
Okay, because sir, can you move one slide before?
Please repeat your words.
Sir, can I see the waveform?
Yes, definitely. That waveform, no, that is known as the return loss and the isolation. So this is the
okay, sir.
return loss.
Not an issue, sir. Sir, and one more doubt is, and how you're fixing that the position to keep the CSRR in the patch?
Yeah, that is a trial and error basis.
Okay, trial and error basis, no problem.
Because
and one more thing is how you are making the dimension of the CSRR, whether it should have the dimensions for 28 gigahertz or
this is especially we have said this in the optimizer. We are using the particle swarm organization. And using that, we have decided the dimension so that the dimension equivalent to the 28 gigahertz can be obtained.
Okay, sir. Thank you.
Okay. So if you make the designs based on the SIW technology, so here you can find the distribution of the current. So current is concentrated at the center, and when you make the CSRR structure, so now change in the surface current distribution can be seen. So this complementary split ring resonator is used here to divert the value of the current from the center position. Okay, now, so this single element was converted into the 4 elements, and the 4-port MIMO was designed. This is the 3D structure of the design antenna. This is a fabricated view of the 4-port antenna. And here we are using the polarization diversity, because if each of the element is kept at a 90-degree with another port. Okay, and as I discussed earlier, that with the help of the substrate indicated waveguide technology, you are able to decrease the value of the mutual coupling. Means you can increase the value of the isolation. So here more than 30 dB of the isolation can be obtained between the ports. And with the help of this SIW technology, if the structure is properly designed, so you can also provide the particular direction of the radiation. So MIMO, along with this SIW technology, is able to provide the coverage of the particular dimension, particular direction in a better way. Now, let us look at the another SIW technology. So we have designed the dual horns. This paper was published in the Physica Scripta Journal in 2025. So this is one of the PhD students who had designed this dual horn MIMO antenna using the SIW technology. So please look at the here dual horns here. Based on the study we obtained, that the dual horns are better to provide the higher value of the gain and the efficiency. So using the study, we have designed the dual horns here. And here you have the gap coupled feed structure, which is used to feed the antenna. So this design was especially done for the vehicular communication for the high-speed trains and the vehicles. So let us look at this design structure here. So dual horns along with the 5G and launch connector ports and Rogers 580 substrate along with the RO3003 substrate. So 2 substrates were used so that the wider bandwidth can be obtained with the help of this SIW dual horn MIMO antenna. So this design is H-plane, right? So if you want to design in the E-plane, so definitely you have to make the aperture here. So in that case, number of layers can increase here, and you have to show the mouth or the aperture to create the E-plane horn antenna. So let us move ahead with this design. As this was designed for the moving vehicles, high-speed trains. So radiation pattern was like the omnidirectional. And because of the number of holes, this zigzag pattern was obtained in the design. And we have also studied about that how the response can be obtained in case of the line of sight communication and the non-line of the sight communication. So because of the time limitation, I have not shown all the scenarios here. We have shown here only non-line of the sight communication scenario when the one dual horn MIMO is kept at the DD distance from the another side-facing dual horn MIMO antenna. So in that case, you can find the increase in the simulation time as well as the return loss and the isolation parameters will increase. So this has become the case of the 4 ports here. So in that case, return loss and the isolation will increase and will take the large memory of the simulation. Okay, now let us move ahead with the next generation technologies again. So the demand of the flexible antennas, because these flexible antennas are especially used, and these are implantable as well as for the on-off body communication, especially in case of the patient diagnosis then emergency rescue, telemedicine, health monitoring, tracking, and for the RFID applications, and for the flexible cases. So these are in the form of the tattoos or can be printed on the cloths. So here, for these flexible antennas, you can use graphene polymers, substrate metal foils, thin glasses, nanoparticles, and textile materials, right? So these can be fabricated with the help of the 3D printing, inkjet printing, screen printing, embroidery, or stitching on the textile, and the chemical etching. So here, there are another kind of the antennas like the virtual antennas. So in on first day, you have seen the case of the boosters, mobile boosters. So those mobile boosters are especially used in case
Pardon,
of
sir, there is one query actually.
yes, yes.
Sir, you are
Yes.
explaining about that the smart flexible antenna which can be used in the cloth and in the some body parts also.
Right.
Sir, is it nowadays we are using some kind of smart watches also? So it is applicable to be inbuilt in smart watches because they are also providing this thing also.
Please remember that please remember that when you want to make flexible antennas, so is Mohit mic off karo.
Yes, sir.
So when you want to use or design these antennas, so please remember the first requirement here that these are implantable on-off body communication. So if you have a patient, for example, and if you want to implant that antenna inside the body of that person having the heart problem or certain critical illnesses, so in such cases, a very small size of the antenna can be implanted in the body of the person. So these are certain flexible antennas, especially used on the cloths as well as on the soldiers' bodies, right? As well as on the patient's bodies. So we can use these antennas for the communication of the signal because these antennas can also be converted into the reconfigurable antennas, right? So especially the flexibility means the bending and the twisting can easily be done. So mechanical deformation is here, and that's why these antennas can be used. Is it clear? Anybody, please?
Yes, sir.
Okay, thank you.
Sure, sir. Thank you, sir. Thank you so much.
And similarly, you have virtual antennas. So in first lecture, you have seen the case of the mobile boosters. You know that the mobile boosters are the certain kinds of the structures are the designs which are used to extend the frequency band, right? So in that case, a single band antenna can be converted into the multi-band antenna. So these virtual antennas means those do not exist in reality. So especially the virtual antennas are made with the help of the antenna boosters. So the first lecture was you have already heard about these antenna boosters. So these virtual antennas can be designed with the help of the antenna boosters, ground plane, and the matching networks. So this matching networks decide the extension of the bandwidth, and the antenna boosters are used especially to reduce the size as well as can be integrated with any kind of the antenna circuits in mobiles and other wireless applications. Okay, now next come to the reconfigurable antennas. So let us look at the reconfigurability and what is the need of the reconfigurability. For example, you are dealing with the satellite, right? So in case of the satellite, the polarization can change easily because the satellite moves in the Earth orbit. So in that case, polarization can change. Similarly, if you want to change the frequency band, right? So reconfigurable antennas are required here. So here the frequency pattern of the polarization can be reconfigured, and this can be done with the help of the photoconducting material. with the help of structural alteration means reconfigurability with the help of the meta surfaces, with the help of the liquid crystals, ferrite. Ferrite is magnetic material. So by using this reconfigurability in the antennas, you can alter the electrical, optical, mechanical, and other properties, and you can find the polarization reconfigurable, or the pattern reconfigurable, or the frequency reconfigurable antennas. So the purpose is to change the complete band, operating band, to change the radiation pattern, and to change the polarization from linear to the circular or to the elliptical. Okay, so this is one of the example of the satellite communication where the polarization will change every time, and if the user is unable to get the signaling, so in that case, the continuity of the signal can be lost. So in most of the cases, we have the dish antennas, right? So these are dish antennas are connected to the satellites, and definitely, if you are watching the movie or listening to the news in the vehicle, or you are using the television, so in such cases, there is a direct connection with the satellite communication. So reconfigurable antennas are used in such applications. So MIMO can be reconfigurable, arrays can be reconfigurable, and these can be used for the cognitive radios also, and all those applications where the beam steering or the beam forming of the radiation patterns can be required. Okay, so there is another application of the reconfigurable antennas. So this reconfigurable antenna is attached with the receiver. For example, the patient changes the position, so definitely everything will change. So in such cases, the multipath fading can be obtained, and polarization mismatch can be done. So if you have the antenna in the reconfigurable antenna is this receiver, so in that case, that antenna is able to receive all the signal from the body of the patient. So the patient has a flexible antenna, right, and the receiver has a reconfigurable antenna. Okay, so if you look at the reconfigurable antenna design, so definitely this PIN diodes are used because we are dealing with the higher frequencies, and the sizes of these pin diodes is very, very small. So teeny structures of these PIN diodes can be obtained. There are so many other things can be used for the reconfigurable antenna designs. So these are battery powered, and definitely because of the change in the voltage, you can find the change in the polarization, change in the radiation pattern, and change in the frequency band. So now let's come forward and think about the dielectric resonator antenna. So as the name indicates that you have the dielectric material, and which is used to make the dielectric resonator antenna. So definitely there is no metallic part, and if there is no metallic part in the dielectric resonator, so definitely the dielectric efficiency can be improved, and the metallic efficiency or the conduction efficiency can be improved because of the low losses, right? So because of the higher value of the conduction efficiency and the higher value of the dielectric efficiency in dielectric resonator antennas, the radiation efficiency can be increased, because the radiation efficiency is a product of the dielectric efficiency and the conduction efficiency. So these all are the things. These are not new, but still these are the most important requirements of the current and the next generation technologies. Those dielectric resonators we have also used for the low frequency application, but here now these are the requirements to reduce the losses at the millimeter wave frequency bands. Okay, so these dielectric resonators can be obtained in different shapes. So hello.
Yes, sir.
Can I continue?
Yes.
Okay, thank you. So here you have different shapes are available because of the ceramic. So white structure is because of the ceramic, and the another shape and the color is because of the polyvinyl chloride. So you can use these materials for making the dielectric resonator antennas. So these are certain dielectric resonator antennas. And as you look at this port here, so this is the SMA connector here. That means these are used for the lower frequency applications. But you are free to use these for the higher frequency application, but the shape will be of very complex size due to the increase in the microwave frequency. And there are MEMS, means micro electromechanical systems. So here the integration with the circuit can be seen. The antennas are integrated in the IC form, and various circuits can be attached with the antennas. Okay, now let's come to the terahertz communication, and the time is limited, so I'll be fast here. As in the 5G, you have the limited spectrum. And in case of the terahertz or the 6G, you have the wider frequency band, 0.1 terahertz to the 10 terahertz in the range. So especially the terahertz antennas are used for the detection, for the aviation, for the defense, for the agriculture, for the medical field and sciences, and for the detection of the infected tissues. So especially these terahertz antennas are used for the detection of the explosives, or the defect in the explosives, and in medicines, or in drugs. So this TNT or RDX or ammonium nitrate requires terahertz antennas. Similarly, the aspirin solubles, solubles and the aspirin caplates are using the terahertz frequency range, and naproxen sodium is also using the higher frequency band of the terahertz spectrum. So here there are so many applications, because the spectrum is used because of the higher data rate, because of the wide frequency band, and these all are required in the case of the space communication, as well as in detection of the objects. So now, if you look at the terahertz antenna designs, so copper is limited in the use, and graphene and the CNTs are used. So if you look at the mobility of the electron, so copper has a 32 centimeters square volts per second, and the graphene has a 2 into 10 to the power 5 centimeters square per volt per second. And the CNT has 8 into 10 to the power 4 centimeters square per volts per second of the electron mobility. So definitely graphene and the CNT are the better choices for the terahertz antenna designs. And the another thing that which kind of the substrate we'll use for the terahertz antenna. So resin, polyimide, so in this slide, this paper was published in IGCS, and this was of Dr. Rashmi Pan. This is she is the second coordinator of your FDP. So in 2023, this was published in the IGCS. So this paper was dedicated to the terahertz antenna design, development, and challenges. So if you read this paper, you can find that so many types of the materials we can use for making the terahertz antennas, different types of the substrates we can use. And you know that this silicon, silico, quartz, gallium arsenide, these can also be used for making the terahertz antennas. So the terahertz antenna, if you look at the terahertz antennas, another application was published in the 2018 in Physica Scripta journal. So what we have done in this terahertz antenna design, that we have created the cylindrical holes in the substrate, right? So because of the creation of the cylindrical holes in the substrate, the new design is known as photonic band gap structure. And because of the photonic band gap structure, you can suppress the higher order modes. You can suppress the surface wave propagation inside the dielectric, and you can also decrease the value of the return loss, and you can increase the value of the gain. So this design was used. And the another benefit of this design, terahertz design, that when you use a photonic band gap structure, so you can reduce the value of the VSWR. So you know that if we decrease the value of the VSWR, then definitely the radiated power can increase and the reflection coefficient can reduce, or the reflected power can be reduced. So if you look at the VSWR of the 2:1, so in that case, 89% of the power is radiated and the 11% power is reflected. If you use the 3:1 of the VSWR, so in that case, 75% of the power is radiated and the 25% of the power is reflected. So if you use a low value of the VSWR, then definitely you can increase the radiated power. So in case of the 1.5:1, you can find the variation in the VSWR and the return loss and the radiated power and the reflected power. The another benefit you can find here in the return loss here. So there is a drastic change in case of the homogeneous substrate and the PBG substrate, that if you use the homogeneous substrate, so return loss is around 20 dB. And if you use the PBG substrate, so return loss can be reduced up to the 45 dB. Okay, gain is also improved with the help of the PBG substrate in the terahertz antenna designs, and the efficiency can also be improved. Now the second design we have extended, in the second design we have extended the application of the first antenna, and we have made the array of the antenna here. So this array of the antenna with the inside feed was used to provide the proper matching so that the gain and the efficiency can be improved. And the 50 ohm of the stub was used in this design along with the photonic band gap. Okay, now let's come to the another design. So in the another terahertz design, what we have done, that we have used the offsetting. We have used this proximity coupled feed. And what we have done here, we have designed this terahertz antennas for the 5.51 to 9.98 gigahertz of the operating range. And we have used the graphene, silica, alumina, and then PEC, perfect electric conductor, means this copper. So with the help of this multi-layer substrate, we have obtained the high value of the bandwidth in this terahertz antenna. Now we have also designed another antenna, and we have also used the same material like the silicon, graphene, alumina, silica, and the perfect electric conductor. So with the help of that, we have designed 5 terahertz to 10 terahertz of the antenna. So now these are certain creations, are the designs of my students, and now let's move further to see the another design. This was published in the MapCon Micro Antennas and Propagation Conference in 2022. So see, this she-shaped hole was created to make the 1.6 to 1.87 terahertz of the frequency band antennas. And then we have also done different types of the terahertz antennas. And this antenna was published in 2024. This is the design of the Rashmi Pant, and in Frequency General, this was published in the February 2024. So what we've done here, we have used rectangular patches and 50 ohm of the stub with the quarter wave section, and 4 patches, rectangular patches we have used in this design to increase the gain. And we have also used the open loop resonator here. So this is again the CSRR, because etching is done in the copper ground. So in earlier design in the SIW, we used the open loop resonator of the rectangular shape in the page, and this time we are using the open loop resonator, means the CSRR in the ground, right? So the purpose of making this CSRR in the ground, that the defect can be created, and because of the defect, diversity can be improved, like the gain, efficiency, and the isolation can be improved, as well as the energy can be concentrated to the main beam. And if you look at this open loop resonator, so these open loop resonator are available just back of the rectangular patches. So here the very low value of the return loss can be obtained like the 35 dB, and the isolation was around 26 dB. Okay, so thank you so much. And if you have queries, so please ask the questions.
Yes,
Anybody?
Prabhu sir.
Yes, sir. Sir, I have few doubts in slide number 32 and 79.
Slide number
32, sir.
yes, please.
Sir, initially you started with insert feed patch, correct? Ma'am?
Right.
Yes. So the first in the array, top two indicates it's going to have the circular polarization, no?
No, 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 no. Earlier, I also stated that this is a linearly polarized antenna, right? So if you are getting the elliptical polarization, so in such cases, you can use the chopping of the opposite corners of the antennas to make the linearly polarized antennas. So elliptical polarization can be converted to the linear polarization. But if you want to make the circularly polarized antennas, so the chopping with the proper dimension must be done, right? So with the proper chopping or the proper dimension, because this chopping is used to convert the axial ratio or reduce the value of the axial ratio for the circularly polarized antennas. The axial ratio must be less than or equals 3 dB.
Correct, sir. Sir, suppose in case if you are making a rectangular slot in the center of the patch with 45-degree angle, so this will make the antenna to a circular polarization.
Yes, definitely. Definitely.
Okay.
Definitely. There are
Okay,
so many approaches are making the circularly polarized antennas. Suppose you have a rectangular page. So at the center of the page, if you move the feed line, so in that case, you can find the location of the 50 ohm, and with the chopping or with the help of the 290-degree feed lines, you can also make the circularly polarized antennas. And if you use the offsetting in your page with the chopping, so you can also increase the value of you can also make the wider circularly polarized antenna.
Okay, sir.
So there are so many approaches. Actually, I have not included the circularly polarized antenna at the 28 gigahertz in these slides. And during my PhD in IIT Roorkee, I also made the 5.8 gigahertz of the circularly polarized antenna. So I request to all of you that if you are interested in reading my paper, so please go through the ResearchGate. Simply type the Leeladhar Malviya or LD Malviya in Google, and you'll find the ResearchGate page disclosed before you. So I have uploaded all the antennas there, all the papers there, and you can frequently download all the papers, and can find the circularly polarized as well as millimeter wave antennas, linearly polarized antennas and all.
Okay, sir. Sir, and slide number 64. Sir.
Yes.
Sir,
Yes.
how you are saying this is 0-degree and 45-degree phase shifter?
Okay, this is a separation from the center line to the top. Right. If you look at the name of the phase shifter, so this is a phase shifter made because of the folded line.
No.
This
First
is a
one is
folded.
not a 0-degree, no, sir.
No, this is possible. Actually, we have not measured these all the things. We have taken this from the text and based on that. Actually, if you want to use these all the phase shifters in your means Butler matrix, so we create the delay line, means the folded delay line, and put that in PSO, and with the help of the PSO, we find the proper value of the phase shift.
Second one is 45 degrees, sir, but first one is not 0 degree, no, sir.
Right, right. So let us look at the slope denoted by this 0.4 mm R. So this slope is also responsible here.
Yes, slope is responsible, and it is mentioning that it is 45 degrees, sir. But first
Yes,
one,
yes. So the
First-
two things are here: the separation between the center line to the top line, and another is the slope. That means the curvature of the this folded line.
okay. Okay, sir, I will check this once when I'm
Yes, sir.
designing this.
Right.
Will
You can
come.
also make the 45 degree, 90 degree of the, because in case of the hybrid couplers, we use the 90 degree of the phase shifters. So if you look at the shape of this 90 degree coupler here, you can find here that the curve or the this line, feed line or the transmission line has a very big slope here.
Okay, sir. Okay.
Right. But don't forget, there are so many modern designs are available here, and the different kinds of the these phase shifters along with the stubs are used to make the compact phase shifters.
Okay. And two more questions, sir. In slide number 79. Yes, sir. For generally, if you're designing an antenna and the radiation pattern, if you're checking at the 0 degree, there we should get the maximum radiation plot, na, sir. Because
Definitely.
if I am seeing in port 1, the first figure,
Right.
the 0 degree having a lesser radiation, because the maximum radiation occurring at it is around 315 degree, and this side it is around 25 degree, correct, na, sir?
Okay, this is not completely the narrow beam patterns. That's why this is slightly wide, and you can find the variation in the gain at the different points. So that's why E field is slightly not smooth here, right? So
Okay.
man lobe is here around this 340, 350 something.
Okay. Okay. And also one more thing is the electric field and magnetic field should meet at the maximum, correct, na, sir?
No, no, no. That is not necessary.
That is not necessary.
That is not necessary.
Okay, sir. One more last question.
Yes.
Sir, if we are designing a meta-surface antenna, meta-surface,
Right.
so I have designed a patch antenna with circular polarization,
Right.
and I have used the material FR4 substrate only. Okay.
Okay.
And I'm getting the gain around 8.2 dBi.
Right.
Okay. So I started designing the unit cell, and it's also radiating at 3.5 gigahertz exactly.
Okay.
Now, if I want to make a meta surface, so many number of that unit cell I can combine and make it as a meta surface antenna. Correct, na,
Right.
sir?
Right.
Now, already the gain is 8.2 dBi.
Okay.
In case if I want to increase the gain, now where I can keep this meta surface, whether on the top of the patch or below the ground of the antenna.
Actually, in most of the cases, those designs I have seen, the meta surface is kept below the page.
Yes, below
Right.
the patch.
And
Okay.
the reason is that if you look at any of the full grounded antenna, right? So this full grounded antenna is used for the half wavelength. Its size is because of the half wavelength, and this is the reflector. So meta surface is also used as a reflector, and that is used to concentrate the energy towards the main beam.
Correct, sir. Yes, sir.
Right. So this is one of the reason. And in tomorrow's lecture, I think Professor Saptrishi Ghosh sir is coming to deliver the lecture on the meta surface. So I think so many doubts will be cleared in that lecture also.
Okay. Because after keeping this meta surface, I'm getting the gain it got reduced. It got reduced to 4.3 dBA. That's what it has.
Okay. So please remember that increasing the meta surfaces doesn't mean that you can always find increase in the gain, because there is a saturation point. So let me disclose about this saturation point here. In case of MIMO array antenna that we design for the 28 gigahertz, so we try to increase the number of elements, number of blocks in array, right? But what happened that after increasing the 12 elements, we obtained that the design is showing the saturated results, and the gain will not increase after that 12 elements. So this is possible because the saturation can be seen in such cases if the energy is not directed towards the main lobe. So in that case, the gain can reduce.
Okay, sir. Thank you, sir.
Okay, thank you so much. Any more question, please?
Any other question from the participants? Or we can conclude the session. I think there are no more questions, sir.
Okay, then thank you so much for the kind listening, patience, and the queries.
Thank you,
So
sir.
if you have any query, you can please write to me, and I'll try my best to show your solutions.
Thank you, sir. On the behalf of the participants and from the MIT Group of Institute Ujjain, I extend my gratitude to Dr. Liladhar Malviya, sir, for delivering such a wonderful session. Sir has explained about 4G, 5G, 6G, terahertz antennas, ECE, and MIMO in very details. Thank you, sir, once again for giving your valuable time and contribution to this FDP. Thank you very much, sir.
Thank you so much, and thank you so much, audiences, for your kind patience. So hope that we'll meet in the future in different courses, conferences, and hope that after seeing such design and listening to these all the lectures, you will be able to make the new generation antennas for the 5G and the terahertz. So thank you so much.
Thank you, sir.
Thank you, sir.
Can I close?
Yes, sir.
Okay, thank you.